Hello, this is our homework for rocket science. My name is Grace Ibsen.
My name is Sophia Ukros.
My name is DeAndre Wilkins.
My name is Khai.
Right here, I sketched out the infrared spectroscopy for the combustion of methane and oxygen. Here where the cursor that is carbon. Right, the blue line represents our products after combustion. So we'll have our CO2 and water, and then we'll have strong peaks for CO2, and then at the like around wave number 2500, and then we'll have strong peaks of between 3200 and 3500 for H2O. And the reason why H2O is a little shorter is because there's like twice as many what's called H2O molecules for every carbon. And then over here for the combustion mixtures, there's we have two types of methane. Mhm. The reason why we don't have oxygen over here for our combustion mixture is because oxygen is a double bond, meaning its valence shell is already like full, and also its electronegativity um like kind of cancels out. So it changes the dipole moments, and it'll make like actually it doesn't change it actually. There'll be no dipole moments, like changes to its dipole moments. So it won't be able to like pick up like the infrared be picked up by the infrared graph. So we won't be able to graph that here. Right here is the X-ray photoelectron spectroscopy. Um, this basically shows us our binding energy and its relative intensity. So like how strong it like pretty much binds, I guess. So right here we have the copper with the copper with the first angular momentum, and then it has a peak at around 950 EVs. And then the other copper we have another with a third orbital momentum with a peak at 932 EVs. And then oxygen and carbon, they'll be relatively the same because they're still in the 1s orbital. So their like intensity is relatively the same. But we'll have 530 EVs for oxygen and 285 EVs for carbon.
Okay, so these are the mass spectroscopies for a natural gas-based rocket here on the left, and on the right is the spectra, for a kerosene-based rocket, such as the Falcon. So the typical fuel composition for a natural gas-based rocket is liquid methane and liquid oxygen as oxidizer, and these rockets usually operate at a mass ratio of 3.6 parts oxygen to 1 part methane, 3.6 to 1. As for kerosene, the fuels often consist of paraffinic hydrocarbons and cycloparaffins, along with aromatics that are kept at low levels, and also oxygen as the oxidizer. These run at a mass ratio of 2.6 to 1. Now, for the mass spectras, if we go back here on the natural gas-based rocket, the field consists of liquid methane. However, the base peak is at CH3 plus because it is easy for methane to lose a hydrogen, and CH3 plus is more stable. And we have lower peaks at 13 and 14, CH plus and CH2 plus, and the oxygen peak is at 32. For the kerosene mass spectra, excuse me, the field is a mixture of long chain hydrocarbons and thus has more complex spectrums with many peaks that consist of alkyl fragments. They're not all included on the graph because there's just way too many, but the base peak is at 57 and the oxidizer peak is at 32. Now for instrumentations, we have infrared spectroscopy, X-ray photoelectron spectroscopy, and mass spectroscopy. As for infrared spectroscopy, up here on the top, here's a picture of the real one. These are all the components in order. Radiation source. It's a solid surface that emits radiation that is invisible to the naked human eye. The interferometer uses a beam splitter and moves mirrors to split the IR beam to create an interference pattern and modulate the signal, which allows frequencies to be measured simultaneously. The sample holder is where you put the sample. The IR beam passes through or is reflected off the sample that is placed in the compartment. And then there's a detector. After the IR beam is reflected off the sample, it's intensely measured by the detector. The signal is often converted into an electrical signal. That electrical signal is then used to create a readable absorption spectrum by the computer. Right, X-ray spectroscopy. The X-ray source generates a high energy photon that is ejected from the surface of the sample, excuse me. The high vacuum chamber keeps the pressure at 10 to negative 9 torr in order to avoid contamination and electron scattering. There's a little typo there, I apologize. Sample storage holds the sample. The electron lens focuses the photoelectrons that are emitted from the sample towards the electron energy analyzer. The analyzer measures the kinetic energy of the electrons. Finally, the detector, it counts the number of electrons in order to produce an X-ray spectrum. And then lastly, mass spectroscopy. The ion source, atoms from the sample are converted into charged gas ions via electron ionization or electrospray ionization, either of those methods. Mass analyzer, the ions are sorted according to their mass to charge ratio using electric or magnetic fields. The number of ions that reach the detector are measured, and the electrical signal is generated and used to form the mass spectrum. The vacuum system helps to maintain a low pressure environment for the ions to avoid collisions when they travel to the detector.
And here we're discussing fuel comparison. So advantages of methane-based fuels are that methane burns very cleanly, which reduces soot buildup, and it makes the engines easier to use. And it also has a specific impulse than kerosene, meaning that it can produce a more efficient thrust. It's also relatively inexpensive and could potentially be produced on Mars using carbon dioxide and hydrogen, which makes it more attainable. With advantages in kerosene, kerosene is much denser and it allows rockets to store more fuel. It can be stored at or near room temperature, which is easier to handle. And also, kerosene engines can generate a high thrust, which makes it more suited for powerful rocket boosters. Some disadvantage of methane-based is that methane must be stored at extremely low cryogenic temperatures, which makes storage more challenging. And it's also less dense, requiring the rockets to have larger fuel tanks. And also, the need for cryogenic simulated systems also adds more weight and complexity to the rocket design. For Kara-based disadvantages, kerosene combustion produces soot and deposits inside of rocket engines, which can reduce efficiency and make engine maintenance more difficult. And kerosene also has a slightly lower efficiency compared to methane, meaning that rockets may need more fuel to achieve the same performance.
So for methane-based versus kerosene-based implications for combustion products and analysis, I found that methane-based rockets usually produce cleaner combustion products than kerosene-based fuels. Methane mainly consists of carbon dioxide and water, which can have a far less soot or solid carbon buildup. This makes post-burn analysis easier because there are fewer contaminated deposits inside the engine, fuel lines, and nozzles. Methane also typically burns cleaner, which makes it easier for engine inspection, reusability, and more reliable sources over multiple launches. And in contrast, kerosene-based fuels produce more soot and carbon dioxide deposits because of the incomplete combustion and cooking. These extra combustion builds make it harder to analyze because professionals must take an extra account for residue buildup, terminal decomposition, and possible engine damage. While kerosene offers a high energy density and provides easier storage, its extra combustion buildup could be detrimental to requiring more maintenance cleanup and a greater risk of failure after multiple uses.